Hey, what's up everybody? Mr. Murray here, back on Mr. Murray's Mathland, and we are doing another AP FRQ, free response question review, this time for area and volume. This is a fairly popular topic, and usually one of the six might be this topic, so I'm just putting a few of the classic kind of ideas together in one problem here. So this is the sort of thing you very well may see on the AP exam, where you're given a graph and given two equations. In this case, f of x is e to the x plus 1, g of x is root x plus 4, and we are given their graphs intersect at x equals 0, which we can see here. They do intersect at 0, and x equals c, which would imply that's right here. Now, I don't know what c is. We're going to have to find that, I'm sure. So let's just dive in here. Find the area of the shaded region. So hopefully by this point in a course you have a knowledge of graph, and you know that f of x is e to the x plus 1. That would be this bottom graph right here, that exponential growth, e to the x with a horizontal asymptote of y equals 1. You can see that's where it flattens out, is at y equals 1. And g of x is root x plus 4. Hopefully you can recognize that is that square root graph shifted 4 units to the left. So this is g of x. And but one thing we're going to need is we're going to need to find where do those graphs intersect, because I'm going to need that for my limits of integration. So one thing you're certainly going to want to find, and let's approach this from a calculator standpoint. Let's assume we have a calculator for this FRQ. Sometimes you don't, and you have to do all of this by hand. So I've input these, I've adjusted the windows. Here are the two graphs, and so I can see that that matches. And if you're not sure which is which and you have a calculator, you can certainly turn on the trace and see you're on the blue graph there. That's e to the x plus 1. It tells you in the upper left. And you can switch between graphs by hitting up or down, and that tells you y2 is root x plus 4. So you can move it around, of course. So whenever you want to find an intersection point, remember you are really solving an equation, and that equation needs to be shown. So I am trying to find where does f of x equal g of x, and you can use shorthand, that kind of thing, or you can say e to the x plus 1 equals root x plus 4 at x equals, and we know it's at x equals 0 if you already want to say that. But the one we're really trying to find, so we're going to do second trace. 5 is intersect, enter, enter, and remember it's going to go to the closest one, so you can either scroll closer to that third one, or you can simply type in a value, a guess if you will. It looks like it's near -3, so it'll go to the intersection closest to -3, and that would be at x equals -2.885. Now remember, you need to be accurate to 3 places, but in something like this, if you're going to use this value to calculate the area and some other things in this problem, you're going to probably want to store it, or at least use more decimals than 3 to make sure your final answer is accurate to 3 decimal places. So this is the C value they're referring to, -2.885193. But you should know how to use the store features on your calculator, because it can be kind of handy. So I'm going to hit answer, which is second negative, and that brings back the last thing we calculated, which was that intersection. And you see it has all those decimals, even more than it was showing on the screen. And I'm going to store that in, I may as well use a C so it's consistent, but you could store it in any of the letters. So alpha program, I'm going to put it in C. And now anytime I want to do an integral or something with that value, I can just type in my calculator C, and you know, saves a little time, and it'll be the most accurate. So our area here, if you just straight up want area between two curves, that is going to be integrating. Integrating gives you the area, and you are doing it from that C value, and you can simply write C, or you could write -2.885 from C to 0 of, and remember, when you are doing these kinds of things between two curves, you want to do the upper minus the lower, the top minus the bottom, to ensure that positive area, right? So no matter where you draw a vertical line here, the top graph is g of x and the bottom is f of x. So we're going to do g of x minus f of x dx, and it is acceptable to use the function names because they're all in terms of x and it's dx. If you're not sure, you can write e to the x plus 1 and minus root x plus 4. So now I'm going to go back to the home screen here, and that's really essentially what I'm going to type in. Math 9 brings up that definite integral, and again I'm going to just be able to type c, save myself a little time, to 0 of g of x. Now g of x, again, I stored in y2, so for shortcuts here you can hit alpha trace, the F4 menu, y2 minus alpha trace y1, all with respect to x, and hit enter, and there is your area. And it's a pretty small area because it's a little slim section there. So our answer, and you just need to be accurate to 3 places minimum, so if you're not sure you can go beyond 3, but that is going to be about 0.719, 0.719, or if you're unsure, go beyond that. But that's a fairly straightforward one, and how they often might start off these FRQs with kind of an easy, straightforward problem. Okay, so part B, we have the same graph, and we don't have to recalculate any of those intersections and things. You can continue using everything you found. But it says for that C, from C to 0, so for this region, let h of x be the vertical distance between these graphs of f and g. Is h increasing or decreasing at negative 1.5? So, they've chosen a value. You can see that the distance between them is increasing, and then of course it's decreasing as you get towards the end. At negative 1.5, it might be kind of hard to judge, and that's why we're not looking for eyeballing it. We're using calculus. So h of x is the vertical distance, and that's that same idea of the top minus the bottom. That's the distance between two curves. Distance is always a positive quantity, so always do top minus bottom. Or you can just do the difference and put absolute values around it, but always easier if you can think and do it without it. So h would be g of x minus f of x. And if we want to know if h is increasing or decreasing at negative 1.5, whenever you want to know if a function is increasing or decreasing, you want to know if its derivative is positive or negative. So if h of x is g minus f, then h prime would be g prime minus f prime. And so if I want to know at negative 1.5, then I'm simply going to do g prime of negative 1.5 minus f prime of negative 1.5 and see what I get. Is that derivative value positive or negative? So I'm going to bring that calculator back. And now we're doing derivatives, so I can do a little math 8, which is function derivative. I'm doing this with respect to x, and I'm really just doing the derivative of g minus f, which again is y2 minus y1. If you didn't want to do these individually, you could find them each individually and then subtract. But I am just doing the derivative of that function at this x value of negative 1.5. And that's giving you 0.093. And make sure to actually answer the question. So it's asking if that distance is increasing or decreasing, and to justify. So I would say the distance h is increasing. Let me minimize that calculator there, sorry. At x equals negative 1.5, and I would just, maybe you think it's obvious, maybe not, but since h prime of negative 1.5 was greater than 0 or positive. The thing is, you never want to leave it up to the grader to guess whether you really knew what you were talking about, so spell it out, make it clear, show off your calculus knowledge. And there we go. Fairly, again, straightforward. Now let's look at a part C. Same graph, same situation, but this time we are saying find the volume of the solid generated when that shaded region is rotated about the line y equals 3. Okay, so whenever you see, you're rotating a region, you're doing a disk or a washer, which is you're going to get a circular cross section. So you're thinking pi r squared. But in this case, you got to ask yourself, is this a disk or a washer? And for a little visualization, y equals 3 is up here. I don't have a ton of room, but it's away from the region. So whenever there's any space in between the region and the axis of revolution, that's going to generate a hole in the middle. When you rotate that region around, this extra space is going to generate a hole in the middle, so you're going to be dealing with a washer. So the washer formula, is pi integral big R squared minus little r squared. Not that you would have to write this for the grader, but for your own sake. So you just have to describe what are those two radii. And if you're a student in my class, you know that I usually like to take a moment and define them before I go right to the integral, but you can go right to the integral. The big radius is going to be that distance from the region to the outer edge of the shaded region. So that would be the distance from y equals 3 all the way to this e to the x graph, which is f of x. And so I could define that as big R is 3 minus f of x. You're describing the distance between those two boundaries, and so top minus bottom describes that distance. You're looking for your small radius. That's the distance from the same axis of revolution, from the middle. That's where the center is. That's where the radius, is generated from. And that's the radius of the hole, the radius of the space. So distance from the axis to the inner edge of the curve. That's the small radius, and that is 3 minus g of x, the distance between 3 and g of x, the square root graph. And so if you can correctly define those, then you're probably pretty good with doing this volume. Just don't forget your pi. Pi times the integral of, it's those same limits. You don't have to recalculate them. We're going from c to 0 of big R squared. Now, you cannot just write R squared minus R squared, because your integral is going to be with respect to x. It's going to say dx. So you have to have expressions that use x. But that's why f of x is okay for shorthand. So that's big R squared minus little r squared. So lots of parentheses here. Right? So just make sure you close them correctly. When you start a set of parentheses, you close that. That's big R, and you square that. Make sure the squared's on the outside, minus little r squared, right? And you're integrating the whole thing, which is why I use brackets, just to kind of make them stand out. But all right, now let's go to the calculator and see how easy this is. So we bring this back. If you're good, you can type all of this in one big step. Pi, math 9, bring back that integral. Alpha c, right? That's where we stored that value. I keep using it. Shortcuts, saves you valuable time. And now again, watch your parentheses. So you have to start a new set of parentheses for 3 minus f of x, and f of x was again y1. Sometimes you might want to make a note to yourself on paper if you're doing that, like which one is which. Squared minus new set of parentheses 3 minus g of x, which I stored in y2. Close that, square that, all with respect to x. And your volume is 6.939 would be okay. Remember, you can simply truncate, or you could round 6.940, or if you're not sure, you could go beyond 3 places and be safe. 6.939775. Go as far as you want, as long as it's a minimum of 3. But there's your answer. Good to go. Hopefully a nice little washer demonstration. And now let's check out the last part that I've made here is same region, but now suppose the shaded region is the base of a solid. So now it's like the footprint. And cross sections taken perpendicular to the y-axis. So as soon as you see perpendicular to the y-axis, that means you're doing things with respect to y, so dy. And cross sections, pay attention to what kind of cross sections you're dealing with. This is rectangles with a height of 5. And take the volume of this, find the volume of this solid. So with these here, first, your cross sections are going to be perpendicular to the y-axis, so they're going to be going in this direction. So one thing you're going to have to do is describe that horizontal distance between those. And since this is dy, you're going to have to turn those functions into expressions involving y. So f of x, let's take each one of those here. F of x is the e to the x plus 1. So instead of y equals e to the x plus 1, let's solve this for x. So x equals what in terms of y? So we subtract 1. That's e to the x. And now we take the ln, the natural log of each side. And so ln of y minus 1 is equal to x. And so that's just another way to describe this curve, points on this curve, but x equals ln of y minus 1. The g of x, which is y equals root x plus 4. Let's solve that for x. Square both sides, so you have y squared equals x plus 4. That will get rid of the square root. And then subtract 4. So y squared minus 4 is equal to x. And so now you have that. X equals y squared minus 4. It's just another name for that curve, but now it's in terms of y. And so again, these cross sections, that distance between there is the base of your rectangle. And with these cross section problems, that distance is usually something important. It's the diameter of a semicircle, or it's the base of an equilateral triangle, or in this case, it's the base of a rectangle with a height of 5. So just take your time to correctly describe that. And with these cross-section problems, the big concept is always correctly describing the area of whatever cross-section you're dealing with. And if you can describe the area, then you integrate it to get that solid volume to add up all those infinite cross-sections. So the area of a rectangle hopefully is pretty easy. That's base times height. The height of each one of these is 5. We've been given that. So it's 5 times whatever your base is. Now the base is that distance between those curves. And so just be careful here. The base is the distance between them, and again, distance when you're going horizontally, to describe it as a positive quantity, you want to do the right minus the left. So the right was that e to the x graph, which is ln of y minus 1. That's the right? We're doing right minus left. And the left is y squared minus 4. So just remember, if that's got more than one term, to use parentheses around it. So you could leave that. You might feel like it's easier to maybe distribute that negative. That's going to be y squared plus 4. You have to clear one set of parentheses at least, but that's up to you. But that is your base. So that is what you are multiplying by 5. So ln 5 times that base, which is ln of y minus 1 minus y squared plus 4. And all of that times 5 is the area of any one of those rectangles. And so your volume is going to be integrating that. Now, here's a problem that you might not have anticipated at the beginning of this problem. The area of this is 5 times ln of y minus 1 minus y squared plus 4 dy. If you want, you could factor the 5 out in front. Frequently we do that. But what are those limits of integration? And that's the problem here in terms of y, so you need those y values. Now remember, we have the y value of this point. The y value of this point is 2. So that upper boundary is going to be 2. But this point was c, and c was, what, negative 2.885 or so. Now, that's the x value of the intersection. So one thing, you can either go back, to the graphs and recalculate the intersection and pay attention to the y value, or just think about it. That would just be plugging c, negative 2.885, into either one of these graphs. If you plug it into either one, you'll get the y value you want. So just don't forget to do that, and I might say, show that. If I want that y value, I'm going to plug it into, I don't know, g. If I do g of c, that should give me the y value on g when x is 2.885. So again, I could go back to the graph, or I could simply hit y2 of c. That's just plugging that negative 2.885 into that and getting the y value of 1.0558. Or notice if I plug that into y1, if I plugged it into the first function, you shouldn't get anything different because it belongs to both graphs. It's where they intersect, so you get the same y value. Again, you might run into this idea of I don't want to round too much because I might sacrifice some accuracy there. So you might store that somewhere else. Maybe I'll store that in D. I don't know. The x value is C. Maybe we call the y value D. And, on paper, you could simply write the three values. G of C was that, and I'm going to call that D. And so now I'm going to integrate this from D to 2. Those are the y values. Or again, you could write 1.056 right here, or if you want to use more decimals, that's fine. But now let's plug that into the calculator. Lots of parentheses here. So math 9 from D to 2. And again, that 5 could have been factored out, but whatever, it could be here. 5 times, start a new set of parentheses, ln of, now we generally on our calculator, use the variable x when you're typing in things, so don't be bothered by that. Ln of x minus 1 minus x squared plus 4, and close that set because you're multiplying 5 by that, and then with respect to x. And notice it's just, you're not squaring anything, you're not multiplying by pi. Sometimes people get a little carried away and think everything with volume's got to be I'm squaring this distance or I'm multiplying by pi. It's just describing the area of whatever that cross section is. So it's a simple rectangle, so just base times height and integrate that. And so we hit enter, and this should give us our final answer here of about 3.596. And there is our volume. And that is the last part. There's a lot of things they could ask with these, but that is where I've chosen to stop this problem. And there we go. But hopefully this has got you thinking about a few of the basic things they ask. So if you have any questions, feel free to ask, and otherwise hang in there and keep working hard.